continuing from the previous lecture, where we had discussed how the second rank property tensor transforms when we for a crystal which has a two-fold rotation symmetry like a monoclinic crystal. So, what we had done in that was as follows. So, I had put a two-fold rotation axis along x 3. The result that we got from this was that the tensor is of this type T11, T12, 0, T12, T22, 0, 0, 0, T33. Now, suppose I put a two-fold rotation symmetry along x1 as well, then how will this tensor transform? So, when I put a two-fold rotation symmetry along x1, so 180 degree rotation about x1 will take 180 degree rotation about x1 will take the axis x2 to x2 prime, will take the axis x3 to x3 prime, and x1 axis will, since the rotation is about that axis, there is no change in the x1 axis, or the x1 prime axis simply coincides with the x1 axis. So, again what we do is we write the direction cosine matrix for this set of axes, and the direction cosine matrix x1 prime coincides with x1, it makes an angle of 0 degrees, cos of 0 is 1. So, this first term will be 0, 1, and x1 prime perpendicular to x2 and x3 axes 90 degrees. So, the next two terms are going to be 0. A21, which is the 2 prime axis making a 90 degree angle with x1 axis. So, again 0, x1 x2 prime making an 180 degree with x2. So, cos of pi, that is minus 1, and then I have 0, and similarly I will have for the x3 prime it will be 0 with because it is 90 degrees with x2 and x3 x1. So, therefore, cos of 90 0, second one is also 0, and it is 180 degrees, x3 prime is 180 degrees with x3. So, cos of pi, so minus 1. So, this is my direction cosine matrix. Let me write down now how the tensor transforms. So, T prime I j equals T I m T j n T m n. Now, since the x3 two-fold rotation about the x3 axis gives me this tensor, I want to look at the off diagonal term, the T12, and see how that transforms. So, T prime 12 equals A1m A2n Tmn. Now, this can be looking only for the non-zero term. So, A1m, the only non-zero term can be A11. So, m is equal to 1, and the only non-zero term for A2n would be when n is equal to 2. So, A22 T12. This would be A11 is plus 1, A22 is minus 1 times T12, hence this is simply minus T12. And we have already seen for the tensor to remain unchanged under the symmetry operation, the only possible value for T12 then is 0. Now, it is easy to show that under the transformation T prime 11 would be T11, T prime 22 would be equal to T22. I am sure you will be able to do this, and T prime 3 would be T 3. So, what kind of a tensor that I will get? The final tensor under the action of two-fold axes around x1, around x3 would be simply T11, now T12 has gone to 0, this is 0, this is T22, 0, 0, 0, T33. Why we did not consider, let us say, the components like T13, T23, because they are already 0 under the action of two-fold rotation along the x3 axis. So, for the tensor to remain unchanged, when I have two-fold rotations at 90 degrees, one along x1, one along x3, the tensor will have only 3 independent components, T11, T22 and T33. And what is the point group? Well, I have two-fold axes at 90 degrees to each other. Recall, going back to crystallography section of this course, when I have two-fold axes at 90 degrees to each other, there would automatically be a third two-fold rotation axis at 90 degrees to both of these two-fold axes, which means that I would also have a third T-fold axis along axis x2. So, the point group clearly is when I have three two-fold axes meeting at 90 degrees to each other, the point group is 2, 2, 2. What crystal system would this point group be associated with? Think about it. It is simply orthorhombic crystal system. So, therefore, for all orthorhombic crystals, a second rank tensor will have only 3 independent components. Now, let us look at another symmetry operation. So, another symmetry operation can be, let us look at a tetragonal crystal system. Now, tetragonal crystal system, what is the axial point group associated with the tetragonal crystal system? It is the point group 4. So, I have a 4-fold rotation symmetry and let us keep it along the x3 axis. So, put a 4-fold rotation symmetry around x3. So, a 90 degree rotation about the x3 axis will take the x1 axis to coincide with the x2 axis. So, this would be x1 prime. The x2 axis will also rotate by 90 degrees and would come here as x2 prime. Now, since the x3 axis around which the 4-fold axis is, the x3 prime axis will just be coinciding with the x3 axis. So, it is easy to figure out what is the direction cosine matrix for this. So, x1 prime makes an angle of 90 degrees with x1 and hence A11 will be 0. A12 x1 prime and x2 makes 0 degrees. So, cos of 0 is plus 1, x1 prime 90 degrees to x3. So, again 0 and similarly x2 prime makes a angle of 180 degrees with x1, and hence this will be minus 1, a2 1, and the other two terms are going to be 0. In the same vein, the third row will be 0, 0, 1. So, this becomes my direction cosine matrix. Let us figure out the terms in this. So, T prime I j equals a1 m aj n t m n. So, T prime 1 1 can be written as a1 m a1 n t m n, and again this will also have only one non-zero term, and which is a non-zero term directly by inspecting the direction cosine matrix. The only non-zero term is going to be a12, which is plus 1, a12, t22, and clearly a12, a12 are plus 1, hence T prime 1 1 would simply be t22. T prime 22 would be a2m, a2n, tmn. So, here the non-zero terms are a21, which is minus 1, a21, t11, both are minus 1, hence T prime 22 would be t11. Similarly, T prime 33, T prime 33, let me write this more directly, a33, a33, these are only non-zero terms, times T33, and this would be T33. What does this tell us? If I look at these two, T prime 1 1 and T prime 2 2. So, looking at these two, it is very clear that T11 has to be equal to T22 for the tensor to remain unchanged under the symmetry operation of fourfold rotation. While T prime 33 after rotation, T33 has the same component. So, now let us look at a few more. T prime 1 2, T prime 1 2 a1 m a2 n tmn, this is equal to non-zero terms a12, a21, t21. Now, a12 is plus 1 and a21 is minus 1, hence this is equal to minus t21, T prime 13, T prime 13, a1m, a3n, tmn, which is a12, a33, t23, this is equal to t23 because a12 and a33 are plus 1. T prime 23, a2m, a3n, tmn. Now, this would be a21, a33, t13. This is equal to minus t13. Let us see what we can conclude from here. That T prime, what we are looking at, T prime 2 3 equals minus t13, and we can also write T prime 13 equals T23. From these two, it is very clear for the tensor to remain unchanged under fourfold rotation. T13 equals T23 equals 0. And then we have also T prime 12 equals minus T21 again for the tensor to remain unchanged, T12 also has to be 0. But T12 is 0 or T21 is 0 because it is a symmetric tensor. So, the final tensor that we will have for a tetragonal crystal system. So, for tetragonal system, I have T11 off diagonal terms are going to be 0. Now, T11 equals T22. So, this will be I will just write it as T11 that these two components are the same 0 0 0 T33. So, in this case now I have only two independent components and all the off diagonal terms are 0. Now, suppose I combine two-fold rotation with a three-fold rotation in a cube. So, I have this is my x1, x2, x3 and I have a two-fold rotation around x3. This I have already seen in the last lecture that this will give me a tensor sigma 11, sigma 12, 0, 0, sigma no. So, sigma 11, sigma 12, 0, then I have sigma 12 again, sigma 22, 0, 0, 0, sigma 33. What happens if I also now put a three-fold rotation about the body diagonal? So, I put the three-fold rotation about the body diagonal. So, basically I am putting three-fold along the direction 1 1 1. And let us see how the x1, x2, x3 axis will transform to x1 prime, x2 prime, x3 prime. So, I am now doing a 120 degree rotation and this is in a cube. So, this I should say that this is done in a cube. So, when I do this, since this is a symmetry operation for a cube, all body diagonals have three-fold, x1 will go to x2 prime, x1 prime. Rather, x1 prime will coincide with x2, x2 prime will coincide with x3 and x3 prime will coincide with x1. So, if I now, it is very simple to write down the direction cosine matrix for this and I am just going to write this because all the new axes are coinciding with an older axis. So, I will have direction cosine matrix as 0 1 0 0 0 1 and then I have 1 0 0. So, this is my direction cosine matrix. Let me quickly solve this, and this time let us use matrices to solve this. So, the transform tensor T prime can be written as A multiplied by T times A transpose. This could be written as 0 1 0 0 0 1 and 1 0 0. And let me now write this particular tensor, for which because the two-fold rotation axis has transformed it to this particular tensor with certain off diagonal terms being 0. So, let us write this. T11, T12, 0, T12, T22, 0, 0, 0, T33. Here I have used sigma sometimes. I have been using sigma and T sometimes interchangeably, but let me make everything T only. And I will write the transpose now. So, transpose would be row into column. So, 0 1 0, then 0 0 1 and 1 0 0. Now, this, so let us multiply first these two matrices. So, what I am going to get? So, first row into the first column, I will get T12, then first row into the second column and I will get a 0. First row into the third column, I will get T11. Now, second row into the first column, this is T22, second row, second column 0, second row, third column, second row, third column T12. Then I have the third row into the first column. So, this is 0, this would be T33 and this will be 0 again. And also I have the direction cosine matrix 0 1 0 0 0 1 1 0 0. Now, if I multiply these two, I am going to get the, so I will get first row, first column, I get T22, first row, second column, I get 0, first row, third column 0, second row, first column 0, second row, second column T33, second row, third column, second row, so third column would be 0. Then first row, first column I get T12, this will also be T12. First row, third column T12. Next, third row, second column 0, then third row, third column will be T11. So, let us look at this particular tensor and let us compare these two tensors. If I compare these two tensors, so let us do a comparison. What does this tell us? That first of all T12 has to go to 0, and if I now, so I have all the off diagonal terms of 0 now. Now looking at the diagonal terms, it basically, if the tensor has to remain unchanged, there is only one possibility, T11 equals T22 equals T33. What does this mean? Well, this implies that for this combination of axes, a two-fold along x3 and a three-fold along the body diagonal gives me a tensor which has only the diagonal terms and all of them are equal. So, there is only one component. So, one independent component, which actually means that this is a tensor which represents an isotropic material. And which particular crystal it is representing? Well, if I go back to this, this is actually nothing but the point group 2,3. This is the point group 2,3, which is one of the point groups, one of the axial point groups for cubic crystals. So, this tensor represents cubic crystal system. So, cubic crystal systems are isotropic with respect to second rank property tensors, and prime example again for that would be that isotropic for, let us say, electrical conductivity. Now, there are other point groups as well for the cubic crystal system. I could have had the following situation. Considering a cube again, x1, x2, x3, and imagine that I have a, instead of two-fold, I have a four-fold rotation, for which also I have solved the problem, and I have again a three-fold along the body diagonal. Well, this forms the point group (432). Well, four-fold rotational symmetry, it has a subgroup. So, four-fold has subgroup two-fold. So, therefore, this will also result into isotropic tensor. You could also solve this problem for the cube, because after all what represents the cube are the four. So, cube is represented by four three-fold rotation axis. So, we can also take let us say a 3-fold here and take another 3-fold along another diagonal, and then see how the tensor transforms under these 2 3-folds, then also you will get the same result that the tensor property is isotropic. I leave this as an assignment for you to work on. Thank you.